Welcome to the, I think, 7th talk in the CS Theory Seminar Series. So today we have Fahad, who's going to talk about parameterized approximations for independent set of rectangles, right? Which is, I think, independent set problem in the rectangle intersection graph, I think. Yeah. Okay, Fahad, yeah, you can begin.
Okay. Yeah. Sorry, I think. Is the slides visible?
Yes, it is. They are visible. Yes.
Okay. Okay. So you can see the title. It is Parameterized Approximation Scheme for a problem which is called independent set of rectangles. And this is a result appeared in last year ESA, and the authors are like Fabrizio Grantoni, Stephen Krach, and I think Weiss, Andreas Weiss. Okay, you will see the name. Okay, so the outline is like I will define this problem, just one problem, and we will see one algorithm, and at the end one open problem. So this will be a very short talk, like probably like 40 minutes. Okay. So what is this problem? Independent set of rectangles. We are given a set of rectangles. They are axis parallel and may not be uniform size. We are also given an integer k, and we want to find the maximum set of rectangles. They are pairwise non-overlapping. For example, these red rectangles are non-overlapping. I'm audible, right?
Yes.
Yes. You're audible. Yes.
Okay.
Yeah.
So this is the problem. Okay, so some assumptions. I will assume that the endpoints of this rectangle or the corners are integers. Okay, I assume that, and that's only assumption. So we are given a bunch of axis parallel rectangles. We are also given an integer k, and the question is: are there k non-overlapping, pairwise non-overlapping set of rectangles? Okay, so in this example, if k equal to 1, 2, 3, 4, 5, 6, 7, if it is 7, then the answer is yes. And I don't know whether you can get more than 7. I think 7 is the largest. Okay, so I hope the problem is clear. You can interrupt me anytime if you find difficulty in understanding some of my arguments. Okay? So what is known about this problem? The problem admits a QP task. That means we can get an approximation algorithm. For any epsilon, it will output 1 minus epsilon times optimally independent rectangles in quasi-polynomial time. And in polynomial time, there is a log and factor approximation. And that is by Chaler, Sook, and Julia Chuzoy. And Marx proved that the problem is W1 hard. And in this paper, Grandoni et al., which is appeared in the last year ESA, they proved that this problem admits a parameterized approximation scheme. That means the following. For any epsilon greater than 0, there is an algorithm whose running time is f of k comma epsilon into poly in n. Here epsilon is a constant. That means that poly n can be n to the power some function of epsilon. And in this, for their algorithm, the running time is like that. N to the power order of 1 by epsilon square is there. So f of k comma epsilon polynomial in n, and it output a set of 1 minus epsilon times min of k comma opt independent rectangles. Independent rectangles means pairwise non-overlapping. So for this talk, I assume that opt is always greater than or equal to k. That means that our algorithm will always output a independent set of rectangles of size at least 1 minus epsilon into k. Okay? So you can start choosing k from 1 to 1, 2, 3, etc. Okay? So I mean, for ease of presentation, I assume that opt is greater than or equal to k. So this is what we are going to see, like this theorem, what is written here. So, and if such an algorithm exists, then it is called parameterized approximation scheme. So notice that this is not polynomial in the input length. It is polynomial in the input length times some function of k comma epsilon. When k is small, and this is faster than, you know, a brute force algorithm. Okay, so what is the algorithm? Now I will move to algorithm. Okay. So this is the input, a bunch of axis parallel rectangles. And what we do is, we first draw a vertical line to the very left without intersecting any of them. Recall that I made an assumption which is like all the corners of these rectangles are integer points. Okay. Then try to sweep from this line which I draw to the right till you just sweep till this point and you find a new rectangle fully contained uh, inside the point you swept. Okay, and then go zero point 0.5 unit backward and draw a line vertically. So you just sweep from the leftmost vertical line and keep going, keep going, keep going. And when you reach this point, you have seen one new rectangle fully contained between the previous line and the place you reach. And then what you do, you just go 0.5 unit backward and draw a line. Okay? And afterwards, you do the same step again. You just move from here, keep going, and you will reach here. So you will see like this rectangle fully contained between the previous line, this one, and the point you reached here. Now you go 0.5 unit backward and draw a line. Okay, keep doing this process.
So just to be clear, just to be clear, Fahad, the second line that you draw, you are looking for a rectangle between the first line and the second, right? Not
Yeah, between the first line and the second line.
okay. Thanks.
Okay, so keep drawing it as much as you can. Okay, at some point it will end, and at the end you draw a right rectangle. Okay, so look at each of these rectangles in the middle, not the leftmost and not the rightmost. Okay, and each of them is hitting on one rectangle that is not hit by other rectangles. Correct? Because I assumed that all the corner points are integers, and this is like, and yeah, this is like 0.5 from here. So if you have drawn already more than say k plus 2, strictly more than k plus 2 lines, then you already got a solution of size k. Is this clear? If it is not clear, please let me know. I will explain once again.
Hello.
Yeah.
Yeah. Can you explain the policy of drawing these lines? Like I just may missed it. Yeah.
Okay. So all the rectangles, the corners are integer points. Okay. And you first draw this one. So can you see my cursor?
Yeah, I can.
Okay. So the leftmost line you draw without intersecting any rectangle. And then you just move from the leftmost vertical line and continue going towards the right. The moment you see one new rectangle fully between this line and the place you reach, you stop. That means this point. Okay, this point you stop, and then you just go 0.5 unit backward and draw the rectangle. So draw a vertical line. Okay, and after drawing this second line, what you do again, go from here, sweep from the second line and keep going, keep going. At some point you will see a new rectangle which is fully between your current position and the previous line, and that will be this position.
Fahad, why would it be that position and not the previous
Okay. Sorry, it won't be this position, it will be this position. Okay.
Yeah, thanks. Yeah.
Okay, sorry, that's my mistake. Okay, that will be this position. Okay, because this rectangle is fully between this line and this position. Clear? And from there you just go backward 0.5 unit and draw a vertical line. And from here you keep doing this process. And
Fahad, one more question.
Yeah.
This is so if you project this to the x-axis, this will be an independent set in the interval graph also, right?
Yes.
Okay, and
okay, what you have drawn here, like, but your solution, your actual solution may not be.
that's right. But yeah, but this particular one will be an independent set for the interval graph also.
Yes, that is true.
Okay, sure. Okay.
So keep.
Only assuming if interval graph is also based on the integer values, right? Not the real values.
Yeah, I mean, I already assumed that the corners are integer values. Okay,
Yeah,
so
integer, then even your interval graph will have integer.
Yeah, so when you project it, the intervals are between integers with this assumption. Okay. So suppose you have drawn more than k plus 1 lines, like k plus 2 lines, then can you see k independent rectangles, one for each of the lines with each of the lines except for the leftmost and rightmost? Because that's the way we drawn these lines. I hope it is clear. I mean, if it is, just interrupt me.
Yeah, it is clear, I think. Yeah.
Okay. So the more, if you have drawn more than k plus 1 lines, then you are done. You already got k independent rectangles. Okay. So assume that you have drawn less than k plus 1 lines. Okay, less than or equal to k plus 1 lines. You can do this drawing in a horizontal way as well, right? And if this happens, then you are done. If you have drawn more than k plus 1 lines, you are done. So now you assume that it is the number of vertical lines is less than or equal to k plus 1. And similar way you can do this process in a horizontal way. And if you have drawn more than k plus 1 horizontal lines, again you are done. So otherwise, what happened is we got a grid kind of a structure of order k plus 1 times k plus 1 at most. Okay. So we got this structure. Now, the important thing here is a partition lemma. Okay, what is the partition lemma? So say, first I have this grid. This grid I have drawn, the method I have explained in the last slide. Okay. Now let R be a solution of size k, which means that R is a set of independent rectangles. Okay. Now this lemma says the following. There exists a solution. There exists a set of independent rectangles, which is a subset of R, whose size is large. By large, I mean it is at least 1 minus epsilon times cardinality of R, with the following property. I will be able to partition these rectangles in S in such a way that each block has constant size. What is the constant here is order 1 by epsilon square. And any cell, what is a cell? Yeah, this is a cell. If you can, okay, in this grid you can see a lot of cells, like roughly order k square cells, or at most order k square cells. Like for any cell in this grid intersects rectangles of S from a particular block only. You pick a cell, it can intersect the rectangles of X from a block Si. If it is intersecting a rectangle from Si, then it will not intersect with another block in S, which is in Sj. Okay. So this is the definition, or not definition, this is the statement of the lemma. Assuming this lemma, are we done? Anyone? Yeah.
So this grid is formed by running the algorithm that you described, both In a horizontal way and in a vertical way, right?
Yeah, the lines are formed by the algorithm I described.
Yeah, and this lemma is stated in terms of that the grid formed by those lines.
Yeah, but the definition of cell depends on that drawing.
And this is true for any epsilon.
What?
This lemma is true for any an arbitrary epsilon, right?
Arbitrary?
Epsilon.
Yeah. For any epsilon, it is true.
Okay.
Okay. For the time being, you just fix an epsilon, an arbitrary epsilon, and then we work on. Okay. So I hope the statement of the lemma is clear. Is it clear?
Yeah.
Okay.
Yeah.
Now, anyone want to make a try assuming this lemma for an algorithm? Maybe I will move on, or anyone is trying. We have plenty of time, so.
Yeah, actually, can you pause?
Okay, I will move on then.
Is a block means S1, S2 are blocks, right, in your language?
Yeah, I mean a partition of S.
Yeah. Okay.
No. So Fahad, so how many are you assuming? Like, how many parts are you assuming? Because I think the index has become 1 for the end, or is it L?
It is L.
Oh, it is L. Is it okay? Yeah. Thanks.
Yeah. I mean some number of parts. Of course, it will be less than K.
Yeah, sure. Like if you're going to be using that later on, I just want to make sure what the index is.
I don't use this L. It is some. Okay, if you
sure. Yeah, no problem. Yeah.
partition, then that is good enough.
Sure. Yeah.
Each part has constant as in 1 by epsilon squared number of rectangles.
Hmm.
And any cell intersects only one of these
blocks.
Okay. And we know a bound on the number of cells. That's what we know.
Yeah, we know the bound on the number of cells, and that's how we are going to get it.
So remind me again, like you actually want to output the rectangles as well, right? Not just the count.
Yeah, I just want to. I also want to output the rectangles.
Okay.
So maybe I move on.
So this lemma is just an existence statement, or there is an algorithm as well? That's not important.
The lemma is an existence statement, and using this lemma, you can make an algorithm.
Right. So basically, for like every cell, you're going to look at all the rectangles that are intersects, and all of them have to be inside the same block.
Yes.
So that way you can basically produce a partition of S.
Yeah.
But I don't know what to do after that. Like what do you get after that?
Okay. After that.
Okay. So from each part, you're going to be choosing only one rectangle, right? And
one by epsilon square many.
One rectangle from each part.
Yeah. So that is constant, right? N choose 1 by epsilon
square. Yeah. Okay. Yeah, I got it. Yeah. Thanks.
So you got it. Okay. So what Karthik was saying is the following. Let Ci be the set of cells that intersect rectangles in Si. Okay. So the cells in Ci will not intersect rectangles in Sj for j not equal to I. So you can guess which are the cells in Ci. Okay. So what you do is, and how many cells are there? K square cells are there. And you just need to choose a subset from it. And that is 2 to the K square. Am I right? And then from this collection of cells, you need to choose like independent rectangles of size constant. Constant is 1 by epsilon square. So look at all the rectangles which are fully contained in the cells Ci, like a union of cells Ci, and you run over all possible subsets of rectangles of size 1 by epsilon square, which is within these cells. And by this lemma, if your Ci is correct guess, you will get 1 by epsilon order 1 by epsilon square independent cells from which is fully in CI. And you do it for all C1 you do it, C2 also you do, C3 also you, sorry, for S1 you do the same, for S2 also you do the same, S3 also you do the same, like that. And L is atmospheric K. So that will give an algorithm of running time 2 to the order K cube into N to the order 1 by epsilon square. Is that clear? The algorithm? Maybe I was a bit fast. If not, then just let me know.
So let me try to. I'm having a bit of difficulty.
Okay.
So for each SI, you guess which are the cells that intersect that SI.
Yes.
Right, and we know this partitioning of CIs are disjoint.
Yes.
Now,
and for the rectangle, okay, the rectangles in SI will be within the cells CI, union of CI, like cells in CI.
Oh, okay.
So that way, like across blocks, they are disjoint.
Okay.
And within the block, it is constant size. So you are brute forcing within a block, within a CI, or within a block.
I see. Okay.
Clear?
So L can be as large as order of K square, right?
What?
L, how large can L be?
L can be atmospheric K, because see, cardinality of S is, atmospheric K.
Okay, yeah, sure, okay.
So number of choices for CI is 2 to the K square, and then L is atmospheric K. So you will get 2 to the order K cube into N to the order 1 by epsilon square. That is the within SL what you are doing. That is what N to the order 1 by epsilon square. So clear? That's a naive one. But we can improve this. I mean, you don't have to do much work for that. K to the order K by epsilon square. So the idea is follows. So previously I choose CI, which is a subset of these K square cells. Okay. Now look at SI. SI contain 1 by epsilon square, order 1 by epsilon square rectangles. Each rectangles have 4 corners. You just guess the cells in which these 4 corners belongs to. So essentially you will be guessing how many cells? 4 times order 1 by epsilon square. The moment you know these corner points, you can find out CI. If you know, okay, these are the 4 points. These are a 4 point, like 4 point of a rectangle in SI lies. One is here, one is here, one is here, one is here. Then all, okay, maybe like I would say like one is here, one is here, one is here, one is here. Then other than these 4 cells, in between cells, this one and this one will also go to CI, because it will be spread like this, your rectangle. So you can guess only those corner points, and then you could get CI. And that guessing will be K to the power order K by epsilon square.
But this times K you have to do again, right? That will be subsumed.
That is why the K in the exponent coming in. So for one CI, it takes time K to the power order 1 by epsilon square.
Or one SI, you're saying, right? One SI.
So yeah, for one SI, for one CI, it takes K to the power order 1 by epsilon square. Because K is the choices, number of choices. Say K choose something like a 4, some order 1 by epsilon square. That will be the points.
So you take one SI and you take each rectangle and you find the 4 corners and guess the. So you basically have 1 by epsilon square rectangle. So 4 by epsilon square corners. So you, finding the CI is all about. There are k square cells. So k square choose 4 by epsilon square or something. But there may be, you find the corners, there may be rectangles, cells between them also, right? As you said.
Like, yeah, but the point is like the moment you know like one rectangle stay like this, for example, then knowing these four cells is enough. Then all the in between should go into CI.
Yeah. So what is the time required to compute CI for a given SI?
You are not given SI, so you are going to guess it. So for each, okay, so you are going to guess the number of cells, which is order 1 by epsilon square cells. And then you are going to guess which are the 4 points corresponds to one particular rectangle.
Yeah, so for a given guessing, for a given guess of, let's say, SI, so how do you compute its CI?
CI would be like,
by looking at the corners, right?
By looking at the corners.
So how much time is
if I have corner 1 here, 1 here, 1 here, 1 here, then all the rectangles between.
What is the time complexity for that?
Okay, so k square choose the number of corners.
Yeah, but not just number of corners. In between things are also coming, right?
That will be like some function of epsilon.
Okay.
Because because the number of boundary corner cells is order 1 by epsilon square.
Okay. So that is why k to the power 1 by epsilon square comes there, right?
Yeah.
So now
k comes there because you have k like a k blocks, at most k blocks.
Okay. Blocks means S1, S2, right?
S1, S2, yeah. So you should be multiplying it. K by 1 order 1 by epsilon square times k by 1 by k to the power order 1 by epsilon square, etc. K times.
Okay.
So given partition lemma, we are done, right? We got a PAS, parameterized approximation scheme, assuming this partition lemma. So what we need, just have a close look, and then we will prove the partition lemma. So the red rectangles are the solution, optimum solution, k non-overlapping rectangles, which we don't know. Okay? And what is the partition lemma says? Look at any cell and look at these four of them. Either if I am going to put these 4 of them into S, then these 4 of them should go into one block. So from these 4 of them, anything which I am going to put into S, they should be going into same block as well, right? Because one G can intersect only from one block. One cell G can intersect from only one block. So if I am going to include, so these rectangles, the set of these rectangles is denoted by R, and S is the one I mentioned there, which is 1 minus epsilon times R, cardinality of R. So if I am going to put any subset of these 4 rectangles into S, then that subset should also go into a particular block. Clear? That is the demand of the lemma. Now to achieve, okay, so I need to find out some rectangles to delete, and then some rectangles like anything which comes within intersecting this cell should go into same block, and every block should be constant size. To achieve this, we use tools from graph theory, mainly from separation theorems of planar graphs. So So now, to prove this lemma, so we will use some tools from graph theory. So I'm going to explain what tool we are going to use it. Okay? So there is some notion of an R division. An R division of a graph G. So graph G is a decomposition into order n by R. R is a constant. Okay, R is an integer, positive integer constant. Order n by R edge disjoint pieces. So you should be able to partition the edges into edges into different pieces, like order n by R of them. And each of this piece should contain at most R vertices. Vertices is the endpoints of these edges within a piece. And for each piece, I can have at most order square root R boundary vertices. Something is called a boundary vertex if it has, if there are two edges, like at least two edges, one is within that piece and one edge is in a different piece, then that is called a boundary vertex. I will just show you some figure. So suppose the graph look like this, and there are a lot of connected regions drawn here. For example, you can see my cursor. This you can think it as a piece. Okay. Similarly, this is another piece, okay? And this is another piece. So each edge participate in one piece, and there are like some vertices which belonging to two of these connected pieces, like connected pieces in this space, like Euclidean space. That is like this vertex, they are called boundary vertices. Like so each, yeah.
Fahad, there are some edges that appear in multiple pieces too, right? Or we assign only to one piece of the two?
You can just assign to one piece.
Okay. Okay.
Yeah, because it is edge disjoint pieces.
Fine.
Two edges are not in one. So, okay, now what are the requirements? Look at each of these, region, small region which I draw. The number of vertices here should be at most R, and the number of vertices which is also belonging to some other piece is at most square root R. Okay? So if I collect all the boundary vertices over all the pieces, it is order n by square root R, because order n by R pieces are there, and for each piece I will have order square root R boundary vertices are there. And so total number of boundary vertices over all pieces is square root R times n divided by R, which is order n by square root R. Okay? So if you notice, if you delete these boundary vertices, which is order n by square root R, then each connected component will have size at most R. Is that clear?
Could you please repeat the last plane?
Okay. Look at all the boundary vertices. Okay. Delete them from the graph. Then you will get a lot of connected components. And what is the size of those connected components? Upper bound on it. In terms of number of vertices. Each piece has at most R vertices. So if you are going to delete all these boundary vertices, then the remaining part will not see anything outside. So the connected components will be either this piece, or this piece may be broken into many more. So its size will be at most R. Is it clear?
Yes.
Okay. And one of the important result is planar graph admit an R division, which means that for look at this graph is a planar graph. For planar graph, we can get this kind of a decomposition. And we don't need an algorithmic result. We just need an existence result. And in fact, one can compute this also.
Fahad, so what should we think about as like R?
R you think as a constant depending on epsilon.
Okay, just a constant. Okay, thanks.
Yeah. So for our lemma.
Yes, yeah. For our use case, yeah.
So that's what I said before. For the planar graph admit an R division, which means that for any n vertex planar graph and an integer R, there exist n by square root R vertices, which are the boundary vertices I explained. So if you delete those boundary vertices, each connected component has size at most order R. Clear? It's just translating what I said before in the previous, like just before, into a different way of saying. Okay. If it is clear, I will move on. Like, yes, this is the important part.
Sure, clear.
Okay. So now what you do is you substitute R is equal to 1 by delta square. Okay. Then what does it say? For any planar graph, and delta is a a fractional number between 0 and 1. Okay? And this delta will depend on our epsilon. Okay. So after you delete delta n vertices, then each connected component has size 1 by delta square. Clear? Just substituting R is equal to 1 by delta square. Nothing else. It was n by square root R, so n by square root delta, n by square root 1 by delta square, which is actually delta n. So what does it say? You can delete a fraction of vertices in a planar graph and make each connected component size constant. Delta n is a fraction of vertices in a planar graph. A fraction of vertices in a planar graph, you just delete it, and then every connected component has size at most a constant. And this constant depends on delta. I hope it is clear. I'm going to move on to the next slide. If it is not, then just let me know. Okay, now we are going to use that theorem. Which one? This one, what is written in the blue. So towards that, we make a planar graph G1 with vertex set being R. R is the solution whose size is K. Okay, an optimum solution whose size is K. So these are the vertices. Now I need some edges. So I'm going to draw an edges between two cells if they between two rectangles if they share some if they are intersecting one cell. So for example, you just focus on one cell. There are like 4 rectangles intersecting here. So I'm going to draw edges as follows: one from here to here, 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 one from here to here. I will not draw an edge from here to here. If I am going to draw an edge from here to here, that may not be planar. Okay. So this is a planar drawing where I don't have one edge between the bottom left corner to top right corner. All other choices I have drawn edges. So similarly, I will draw for this cell where I draw here. I will draw here. I will draw an edge, and for this cell I will draw here. This cell I will draw here. I can actually draw here.
Yeah. So suppose for a cell you only have 2 rectangles overlapping that cell. One is at the bottom left and the other is at the top right. Then will you draw an edge between them?
You can draw, but for the first step I don't draw.
Okay.
But even drawing that, it won't harm anything.
Okay.
Good. it won't give asymptotically anything better, because we have to consider these kind of soft cells as well. So the second step will take care of that. So this is the first step. Okay. So I have drawn. So now look at this graph. This is a planar graph, because I have not drawn any edges which are crossing. Clear? So the planar graph will have vertices, which is R. Vertex set is R. Now, what does the R division?
Fahad, sorry to interrupt. So R is the same R that we saw in the previous slide, right? In the planar R.
An optimum solution, a hypothetical optimum solution.
So now it corresponds to some set of rectangles.
Yeah, some set of independent rectangles.
Okay. Okay. So
and that is what
independent set of non-overlapping set of rectangles.
Yeah, independent means non-overlapping.
So is it possible? Just to understand, is it possible that in this figure now, if you take any cell, there are at most four rectangles that are overlapping that cell? Is it possible that there are more cells overlapping?
No.
Rectangles.
No, there will not be any rectangle which is of this form.
That's the question. Yeah.
Yeah, because of the way we draw the lines.
Okay.
The grid construction guarantees that.
Okay.
So no rectangle will be like, without hitting the corner, there won't be any rectangle.
Sure, sure.
And that is guaranteed by our construction of the grid.
Yeah. So I think, for instance, if there was such a rectangle like you indicated, the horizontal line construction would be a contradiction to the horizontal construction.
So there could have been another line hitting that.
Right.
Okay. Yeah, that's a good point. Yeah, I missed that. Okay. So every rectangle will be hitting some corners, not somewhere in the middle.
Okay.
So this is a planar graph, easy to see, right? The way I draw edges, it is a planar graph. Now, what you do, what is the R division tells us? I can find delta R, like for any delta R vertices in D1. D1 is the graph, like where vertex set is R. Such that each connected component in G minus G, okay. I call D1 be this set of delta times cardinality of R vertices. Okay. Such that G1 minus D1, for each connected component in G1 minus D1, its size is order 1 by delta square. That is guaranteed by our previous, result on planar graph. R division, where you substitute R is equal to 1 by delta square. This delta will depend on epsilon that we fix later. Okay. So what does it say? You can delete some rectangles here, not too many, only delta times cardinality of R many. And if you look at any cell, I cannot, any cell, and if I have two blocks, two connected components, then one will be intersecting here and one will be intersecting here. For some cells, it will be intersecting only from one connected component, and for some cells, it may be intersecting from two connected components. If it is intersecting from two connected components, how does it look like? Look at this green cell. That is, one is here in the bottom left, and the other connected component will be intersecting on the top right. Clear? The way of construction. Because if I have another, so this connected component also had a rectangles here, then there could have been an edge like this. And which means that this and this part of same connected component. So we got some property which is almost the property of the cells we want. Like this cell may intersect more than one connected component, like two connected components. one, and if it is intersecting more than one, then one will be hitting on the bottom left and one will be hitting on the top right, where you can assume that these connected components will give you blocks. Okay, so what we do, we again do this procedure, that is, we construct a super graph G2 of G1 minus D1. G1 minus D1 is this graph. Okay, so I just draw edges of this form. So I know that there is nothing like no other ones intersect. Okay, if something is intersecting here, this will not be in a connected component containing this, because it will have an edge here. Sorry, there will not be anything like this here and here. If it has, then all of them will be in one connected component. So look at the cells which is intersecting two connected components. Then the structure will look like this. So I draw an edge like this.
So just 1 second, Fahad. So you are using basically that partition lemma, which says that if there are, like, you are deleting 1 by deltas, sorry, n delta vertices, a fraction of total number of vertices, and you get each component of size order of 1 by delta square, right?
Yes.
So yes. Here you are now in this rectangular thing. You're constructing a graph out of it and using that lemma, a planar graph out of it and using the lemma. But that lemma is existential again, right?
That's existential. We only need, I said, I just need to prove partition lemma, which is existential. You can use that existential partition lemma to algorithm, and that we have.
Okay.
So, for example, I don't know this red, right? If I know the red, I'm done. The red rectangle.
Okay.
So some cells may be intersecting two connected components. So I'm going to make a new planar graph, which is a super graph of G1 minus D1. Okay? So where I draw edges of this form. Okay. So I got a new graph G2. Again in G2, I can apply that R division, which says I can delete delta times the remaining set of vertices, which is at most delta times cardinality of R, such that after I delete those vertices, each connected component has size order 1 by delta square. Now I should have been deleting these vertices. These vertices corresponds to those rectangles. So now after I do the second deletion operation, look at any cell. Okay, and the rectangles intersecting on these cells, they will be in the same connected components here, and the connected component size is order 1 by delta square. So first construct G1 and delete delta R vertices, and you got a graph G1 minus D1, and then again make like where each connected component has size order delta square. Sorry, order 1 by delta square, and then you make a super graph of this graph G1 minus D1, where you will be adding some edges between two connected components. So now in this super graph, the property of like connected component size is bounded by order delta 1 by delta square no longer exists. But after you delete, again at most delta times R vertices, again the connected component size will be at most order 1 by delta square. Now, if you look at a particular cell, and if you see more than one rectangles intersecting on that cell, then rectangles intersecting that cell, then those rectangles will be in the same connected component. Is that clear? If you have any doubt, just ask me. Otherwise, I will move on. So I guess it is fine. So I will move on.
Yes.
So, yeah, you have a question. Subru, do you have a question?
No, I don't have a question. No.
Ah, okay. Okay. So
someone else came in between. I think I don't know who it was. Yeah.
Okay. Okay. So how many vertices we deleted? So in the first step, delta times r, and in the second step, at most delta times r. So the remaining number of vertices is 1 minus 2 delta times r, capital R, the cardinality of r. Clear? And each connected component has this property, like size bounded. And each cell will intersect only from vertices from one particular connected component. And substituting delta equal to epsilon by 2, you are done. Because the remaining set of rectangle is 1 minus 2 delta, at most 2 delta times cardinality of r, many you have deleted. So the remaining is 1 minus 2 delta times cardinality of r. So when you substitute delta is equal to epsilon by 2, how many left after deletion in these two steps? 1 minus epsilon times cardinality of r. And that's complete the proof. Like the connected components will give you the partition of the remaining set of rectangles. Okay, so we have proved this lemma. So this I explained. Okay, so the number of choices for Ci is k to the power order 1 by epsilon square. This is the second like improved algorithm rather than the naive algorithm which we explained. Now, other than a polynomial, parameterized approximation scheme, we can get a kind of a approximate kernelization. How we get? The choices for each Ci is same. The choice for C1 is same as choice for C2. So for each of such choices, the number of such choices is k to the order 1 by epsilon square. So for each such choices, I just check whether there exist independent rectangles of size at least 1 by epsilon square. Then I collect that. Then I collect, the number of choices, many steps of this. So if I collect k to the power order 1 by epsilon square times 1 by epsilon square such rectangles, then that set of rectangle will contain a solution of size at least 1 minus epsilon times k. Is that clear? Maybe I went a bit vague and fast. So previously what we have said, for each Ci, I have a choice of getting cells. The number of choices of getting Ci is k to the power order 1 by epsilon square. And the moment I know like one choice for Ci, what I'm going to do is, are there 1 by epsilon square many independent non-overlapping rectangles within that Ci? And then if them, I just choose it. Okay? So instead of like guessing for each C1, C2, C3, etc. separately, I just run over all possible choices for this Ci, and then I will collect for each of the choice at most 1 by epsilon square many non-overlapping rectangles, and I collect them from all the choices. So how many rectangles I could have got? The number of choices times 1 by epsilon square many, which means that among those set of rectangles, I have a solution containing 1 minus epsilon times k. And this is some sense a kernelization. So we could actually get an approximate kernelization as well, not only an FPT algorithm. So in the next slide, I will summarize it. The first one, we got an algorithm which runs in this time. The second one, running in polynomial time, I can get a collection I prime of rectangles of this much size, such that in this one, I have a solution of size at least 1 minus epsilon times k. Opt is equal to k. Like maybe I need to change opt equal to k. And then this kind of algorithm is called, approximate kernelization. Here, we are not solving it, but we are just compressing the size of an instance. And so since we have it for all possible epsilon greater than 0, we could say that this is a approximate kernelization scheme where the size is polynomial size, which represent the size of I prime. So we can actually get a parameterized approximation scheme, actually a polynomial size kernelization scheme, like approximate kernelization scheme as well. And that's about the algorithm. And what is left with is open problem, right? The open problem is this problem admit a p-task, that is polynomial time approximation scheme, not FPT time approximation scheme, or at least a polynomial time constant factor approximation algorithm. The best approximation factor is order log n. And the answer to the above question is most likely yes, as there is a QP task for the problem. But we don't have a proof for it. That's all. The only thing is just finding the proof. And that's it.
Did you mention like what is the idea behind the QP task at all, or did I just?
This I don't know. This is a different paper.
Okay, I see.
And I think that's appear in Soda or Fox.
Okay, sure.
I will just all these.
Was it the same set of authors or?
No.
Oh, okay. Andreas Wies and Adam Sheck. Yeah, okay.
If it's Wies, then it must most likely be some dynamic programming thing, I guess.
I wouldn't be surprised. Yeah, he's now in Chile.
Okay, but the point is like all these, like I think some of them are in Fox, some is in Soda. So
okay.
Yeah, you will get a good reward for solving it.
Let's see.
So Fahad, with the kernelization thing, can you also say that it's like parameterized FP task? Because we just brute force on the kernel, then would we call that like a parameterized FP task?
Yeah, I mean it's same as the result PAS, right? Like parameterized approximation scheme. I mean
no, but in the parameterized approximation scheme, the exponent it was n power the exponent dependent on epsilon, right?
Yeah.
Here, if you brute force the kernel, it will be like f of k comma 1 by epsilon times polynomial in n.
Yeah, but it's a good question. But to make this kernel, you spend n to the power function of 1 by epsilon square.
Oh, okay. So when you said polynomial, okay, it depended on epsilon again. Okay.
Yeah. So reducing that's also a good like sub questions.
Okay.
But the long-standing open problem is p-task.
And the other thing that you mentioned is constant factor approximation, right?
Yeah, at least that, like anything little of log n is also good in polynomial time, because that's the best norm. Where like instead of log n, maybe constant is. So
yeah, let's thank Fahad. Thank you, Fahad. A nice presentation. Any
Thank you,
other
Fahad.
questions? All right, if there are no other further questions, thank you all. Yeah, thanks for the next.
Bye.
Nice talk, Fahad. Thanks so much. See you. Bye.
Bye.
Thank you, sir.
Thanks.